Welcome to the presentation of thermochemical fluids in greenhouse farming, short TheGreefa. TheGreefa Training Programme, Module 2, Demonstration of the Technologies. Here's an overview of the following presentation: air control in the greenhouse, design of the absorber, results, drying process, TCF characteristics, and drying process results. In Module 1, we introduced TheGreefa's use of liquid desiccants, known as thermochemical fluids, short TCF. These fluids, typically salt solutions like sodium hydroxide or magnesium chloride, share a common trait. Their hygroscopic properties allow them to absorb water vapor from the air, simultaneously releasing sensible heat converted from latent heat stored in the vapor. To illustrate the process, absorbing 1 ton of air humidity in the greenhouse releases approximately 680 kilowatt-hours of heat due to the phase change involved. This humidity is then condensed into liquid water. The effect is that the greenhouse is both heated and dehumidified. As the TCF absorbs water, it becomes diluted. Once the TCF reaches a certain level of dilution, it cannot effectively absorb more moisture and requires regeneration. During regeneration, the absorbed water is driven out of the TCF. Diluted TCF can be stored for extended periods without significant losses, awaiting regeneration when heat becomes available. Heat sources could include sunny periods or residual heat from other processes. Transporting the diluted TCF for regeneration can occur on-site or elsewhere without thermal losses. Although no thermal energy is stored during transport, the potential for releasing thermal energy remains. For regeneration, also, reconcentration, approximately 680 kilowatt-hours of energy per ton of evaporated water absorbed, must be reintroduced into the system. Regeneration typically occurs at temperatures below 60 degrees Celsius, depending on the phase equilibrium between the TCF and the ambient air pressure. The water released during regeneration can either be released as water vapor absorbed by drier air or condensed and recovered as pure water. Concentrated TCF can be stored as needed for long periods. This system effectively manages greenhouse humidity and heat, optimizing growing conditions while recovering and reusing thermal energy. TheGreefa is used in continental climate regions to regulate temperature and humidity inside greenhouses. Its use can significantly lower the energy needed for heating, a crucial factor in these areas. By managing humidity without needing to open windows, TheGreefa minimizes heat loss to the outside environment. Additionally, the absorption process itself releases heat, further reducing heating energy requirements. To illustrate, a traditional greenhouse is shown on the left, contrasting with the TheGreefa equipped greenhouse on the right. In the TheGreefa system, the regeneration process occurs outside the greenhouse, where humid air is released into the atmosphere. In continental regions, there is typically no need to recover water from this process. Overall, TheGreefa optimizes greenhouse conditions in continental climates, enhances energy efficiency by reducing heat loss, and efficiently controls humidity without compromising internal thermal stability. The absorber is a straightforward component, a plastic scrubber filled with random packing, necessary to withstand the corrosive nature of the TCF salt solution. Air flows from bottom to top, while TCF flows in the opposite direction, from top to bottom. The packing enhances contact surface area and prolongs contact time between the air and TCF. To ensure effective absorption, it's crucial to maintain a minimum residence time for both fluids inside the absorber. This is achieved by setting a maximum air velocity and a minimum TCF float density. In the Swiss demonstrator, a residence time of 1.5 seconds is achieved with specific parameters. An air velocity of 1 meter per second for an empty absorber, and TCF flow rate of 12 cubic meter per hour and square meter. Based on these parameters, the absorber has a diameter of 0.4 meters and an active height of 1.3 meters, where air and TCF can interact. The slide illustrates the simple construction. On the left, a transparent prototype used at the facility of the Zurich University of Applied Sciences shows the active height filled with packing, shown in white. On the right is the absorber used in the Swiss demonstrator. The absorber is divided into several colored sections, as shown in the picture. Yellow. TCF distributor ensures even distribution of TCF throughout the absorber. In blue, active part, random packing. This section is filled with small random packings where the absorption process occurs. In red, floating packing prevents aerosol formation within the scrubber. Purple, the sump collects TCF from the active part and pumps it back to the absorber. Green at the top, the emister prevents liquid droplets from exiting the absorber. Air enters the absorber through a fan located at the air outlet. The absorber operates just below ambient pressure, preventing untreated air from leaking out. On the TCF side, TCF is drawn from the pump by a recirculation pump and pumped through a heat exchanger to the absorber head, through here. Here, it is evenly distributed over the packing by the liquid distributor. The scrubber sides entirely within the sump and has outlet openings for the salt solution on the bottom. This setup isolates the air in the scrubber from the atmosphere in the receiver tank, allowing it to operate openly within the greenhouse environment. An overflow in the storage tank between the scrubber and the solution circulation pump ensures uniform flow, preventing uneven TCF concentration. All parts of the absorber that come into contact with TCF are made of polypropylene or polyvinyl chloride for corrosion resistance. The heat exchanger is coated with perylene on the solution side. The air humidity is controlled by the TCF concentration, while the air temperature is controlled by the TCF temperature. Maintaining a specific TCF concentration inside the absorber is crucial for effective humidity control in the greenhouse. Only with the correct TCF concentration can the absorption process effectively manage air humidity. If TCF becomes too diluted, it loses its ability to control humidity. The process for the humidity control is implemented as a batch process. When moisture levels exceed the desired range, as indicated by measurement point MR1, the TCF sump is drained and refilled with concentrated TCF. Air temperature is monitored at the absorber outlet TR2. If the temperature falls outside the required range, either too low or too high, the TCF is either heated or cooled in the heat exchanger illustrated in the diagram. In the Swiss greenhouse setup, this heat exchanger functions as a TCF water heat exchanger. The desorber is used to regenerate, also known as concentrate, the diluted TCF. Structurally similar to the absorber, the desorber operates under positive pressure with a fan at the air inlet. Air enters from the bottom and exits at the top. A heat exchanger provides the energy required for the desorption process. The temperature inside the desorber during regeneration, where water evaporates from the TCF into the air, influences the velocity needed to achieve the desired TCF concentration. The desorber operates also as a batch process. Normally, the desorber sump is empty. During regeneration, it is filled with diluted TCF recirculated from the back to the sump. Density measurements and solution temperature determine the TCF concentration. Once the maximum TCF concentration is reached in the Swiss demonstrator, it's at 32%, the desorption process stops. Concentrated TCF is then pumped from the desorber sump into a storage tank for concentrated TCF. For more details, please refer to the Cordy's webpage and the document titled Concept for a Fully Automated System and Operating Manual. You can access the document through the link as shown. The results presented in the following slides are from the Swiss demonstrator. This greenhouse spans 600 square meters and is located near Zurich, Switzerland. It is specifically designed for cultivating orchids. Rather than being placed directly on the floor, the crops are situated on tables as shown in the picture. Based on data collected and interpolated over more than a year, the energy savings brought to Swiss greenhouses by TheGreefa technology have been estimated. In the pie chart, 100% represents the thermal energy that would have been required in the greenhouse without TheGreefa. The red segment indicates the energy saved by TheGreefa through humidity control via absorption instead of releasing warm and humid air outside. The blue segment represents the thermal energy releasing during the absorption process. This energy is necessary for heating the greenhouse, but does not need to be supplied directly by the operator. It is used for regenerating the TCF at low temperatures, energy that would otherwise be wasted. One of TheGreefa's key features is the ability to store this energy for long periods without loss, in the form of concentrated TCF retaining potential rather than just thermal energy. Lastly, the gray segment shows the thermal energy that the greenhouse operator must actually supply. However, the situation is reversed when considering electricity consumption, as shown in the graph. With the implementation of TheGreefa, electrical consumption increases by approximately 24%. It's important to note that the rotating components, such as pumps and fans within TheGreefa, have not been optimized for their electrical efficiency. Additionally, the design of air ducts and heat exchangers prioritized thermal performance, resulting in significant pressure losses. Therefore, there is potential to reduce this additional consumption through optimization efforts. When evaluating the overall energy balance in the Swiss greenhouse, it's evident that electrical energy has a smaller impact compared to thermal energy. If we exclude the energy used for regeneration, whether because it's managed separately from greenhouse operations or remains otherwise unused, the total energy savings exceed 50%. Even when factoring in the regeneration energy, substantial savings of around 35% are still achieved. Based on measured data of concentrated TCF used in the demonstrator, the blue line, the production of concentrated TCF, the green line, was simulated using warm water generated by thermal solar panels located near the greenhouse. Approximately 100 square meters of solar thermal panels are required for the Swiss greenhouse, which is about 1/6 of its total surface area. Interestingly, TCF regeneration occurs year-round because it depends on the temperature difference between the air and the TCF rather than the absolute temperature. Production experiences a slight decrease during colder months due to shorter days and increased cloud covers. Based on the quantity and usage patterns of TCF used and regenerated, the minimum required size for TCF storage has been determined. Only one storage unit is needed, as the different densities of concentrated and diluted TCF prevent them from mixing. During the cold season, TCF usage is high while regeneration is slightly lower. By the end of this season, March, the storage is fully occupied by diluted TCF. Conversely, at the end of the warm season, due to opposite conditions, the storage is entirely filled with concentrated TCF. The required storage volume is approximately 175 liters per square meter of greenhouse area. The drying process is very similar to the process for air humidity and temperature control, with the goal of dehumidifying the air without altering its temperature. This application is detailed in the slide. Air is dried in an absorber in counterflow with concentrated TCF, avoiding heating to prevent potential harm to leaves or vegetables and maintain their quality. The absorber can be configured similarly to the one used in the greenhouse. In a closed cycle, the dry air released is directed into the drying chamber to extract humidity from the vegetables. The diluted TCF can be stored without thermal losses and regenerated when renewable heat, such as solar energy, becomes available again. Compared to conventional plants using compression dehumidifiers, absorption-based dryer limits electrical energy consumption to fans and liquid pumps. The required thermal energy can be entirely provided by a low-temperature heat source, making it fully renewable. After regeneration. This energy can also be stored without losses. The choice of TCF for use in the drying plant is different from that used in the greenhouse. The slide illustrates the equilibrium line between various TCFs and humid air. Dashed lines represent air with different humidity levels. Intersections points between the solubility line of TCFs and those of the air indicate the minimum achievable humidity at a given temperature. For instance, at 20 degrees Celsius, using a magnesium chloride solution, the maximum dehumidification level doesn't go below 35%. Magnesium chloride was selected for the greenhouse due to its availability and low cost, despite its limited hygroscopicity. At 20 degrees Celsius, the air humidity cannot be reduced below 35% relative humidity. While this humidity level is too low for plant cultivation, it is too high for a drying process. Expensive alternatives like lithium bromide or lithium chloride solutions could be considered. For the drying process, we aimed to find and test a TCF with better hygroscopic properties than magnesium chloride, while keeping costs affordable. Additionally, the TCF needed to be compatible with the food industry. After analyzing the characteristics of different TCFs, we choose sodium hydroxide, which is widely used in baking and meets these requirements. One challenge with using sodium hydroxide is that it reacts with CO2 in the air to form carbonates, which then precipitate. This means the precipitate needs to be removed and the sodium hydroxide replenished. This problem can be minimized, if not eliminated, by recirculating the air in a closed loop. In the diagram, CO2 reacting with sodium hydroxide during the regeneration process is shown in the blue. The regeneration was carried out at the Zurich University of Applied Sciences plant as an open cycle, with new ambient air continuously supplied. In this case, continuous replenishment of sodium hydroxide is necessary. In the absorber used for dehumidifying the air drying process, the air is continuously recirculated, as shown by the red line. CO2 reacts with sodium hydroxide only initially. Once its level falls below the reaction threshold, it is no longer removed. Therefore, the sodium hydroxide does not require replenishment. The carbonates formed precipitate in the sodium hydroxide solution and can be removed at the end of the drying cycle. The concentration of TCF used in the laboratory tests was initially 50% and decreased to 44% by the end of the drying process, without being replaced throughout. As a result, the absorption power was higher at the beginning and lower at the end. However, in the final stages, removing the remaining moisture from the nearly dried herbs is more challenging. A high concentration of TCF is not strictly necessary at the beginning of the drying process, but becomes essential in the final stages. Therefore, the concept illustrated in the slide is proposed. The process starts with a diluted TCF, which is then replaced in subsequent phases with increasingly concentrated TCF. This can be achieved by reusing the TCF from the final step of one batch of herbs in an earlier step of the next batch. Only when the TCF is so diluted that it can no longer absorb moisture will it be sent for regeneration or to be diluted TCF storage. Using a step process can reduce the volume required for storage. As illustrated in the slide, the energy required for regeneration remains the same since the same amount of water needs to be evaporated. The specific energy consumption of the entire plant, including the regeneration of the TCF, has been estimated and compared with a real plant. In the picture, the blue arrows represent electrical energy, and the red arrows represent thermal energy. Considering that the regeneration uses otherwise unused thermal energy, essentially free energy, the specific energy demand of the TheGreefa is clearly lower than that of conventional drying with a dehumidifier. It is important to emphasize that the significant advantage of the TheGreefa is not only its lower energy requirement compared to a conventional plant, but also that the thermal energy required is decoupled from the drying process. This thermal energy can be entirely sourced from renewable energy or low temperature waste heat that would otherwise go unused. Additionally, TCF can store thermal energy indirectly for a long time without any energy loss. Thank you very much for your attention. Your contact for question is Serena Danesi, Research Associate at the Zurich University of Applied Sciences and coordinator of the project TheGreefa.